Oh, okay. We're officially starting, although I've been talking before I started the recording, so I'll maybe do some trimming on the video before I process it later. But welcome to this Wednesday the 14th. We're just talking a little bit about the lab and processing WAV files. Those of you not in the lab, you will be working with speech, and you'll be working with real-time audio using Pi Audio Helper on the first project. So some of the things that we went through last week for the lab to get it to work under this newest version of Python, which is what most of you ended up installing when you did this combined install of Julia and Python together. You got, just like I have on my laptop, you got version 1, or I mean in Python we have version, I guess it doesn't say it right here. We have Python 3.10 though, 3.10 something or another. So, and that caused some issues. So I'm going to talk about that. As long as I'm on this screen right now, I'll just talk about things that I'm now changing in the way I do the notebooks. And this notebook is one that I've created a few years back, but I'm updating it for fall 2022, and it's not posted up there. I'm going to replace the chapter 2 fall 2021 later today, and then maybe do some Julia examples in another notebook. But at any rate, it used to be that there was this command, and it's called a magic command. Anything with a % sign in front of it in the context of IPython, which was something created quite a few years ago, actually by a PhD student at the University of Colorado Boulder. He created IPython as a shell environment, and the shell environment is something that you'd be able to run just if I opened up a shell, and suppose I'll just switch to on this machine, a virtual environment called com39, which means it's Python 3.9. But this is an environment that, getting started with Python, that document I have on the website goes through the use of IPython, which is just an enhanced shell that you see right here, that you can do all the things you can do in the Jupyter Lab notebook. All of these things occurred in fairly rapid succession, starting about the time I was writing my Signals and Systems for Dummies book. I started following it, and it was going pretty rapidly. So the idea of IPython as a convenient shell for working in Python rather than just the plain old command prompt was born way back then. So in other words, if you just type Python, you get this, and notice there's a difference. You just have the 3 greater than signs. It's telling you what version, and so on and so forth, but you don't have any neat editing features. And that is the way Python pretty much started, at the command line, and you would just run scripts and so on and so forth. And there might be at least one of you in this class that's the way you do anything with Python. I mean, I've always had somebody that's been very much not interested in learning something new, but these are things that moved it along from being just simply a Swiss Army knife of tools, and that's what I look at Python. It's very broad. It's, you know, long and narrow or thin, in that it provides capabilities across a broad spectrum of programming in terms of scripting, and that's what I thought it was for the longest time in my life. And then somebody one day asked me, do you think Python will ever replace MATLAB? And this was at Real-Time Logic, which is now Kratos, when I worked there on a sabbatical in 2005 to 2006. And I said, I don't know enough about it. But then by the time I moved on to work at Emergent a little bit later, and was forced into kind of learning Python, not because a company wanted me to, but because I wanted to use it for graphics when I was using Octave, which is an open source version of MATLAB. I soon realized that IPython was the way to go, and it was just a command window like I was showing here. And then a whole lot of other things started to happen. And the notebook came along at the same time. Oops, I forgot to make it a function when I exited. So now I'm back. And then it eventually grew up. This is again in my other document. I'm just going to show you the history though. If you were not launching Jupyter from within Julia, you'd be doing something like this at the command line window. But you could also launch a sophisticated looking console called the Jupyter Qt console. And right now you can see I don't have it installed on here, so I'd have to go and install it. But it's pretty much how I wrote my book. There's pictures of it in this document over here. So the Qt console would look something like, let's see, I'm pretty sure I showed an example of it. You know, where I talk about environment and choices. So Qt console, there's Jupyter Lab, IPython console I already showed you, but Qt console looks like this. It's almost just like what you have inside a given cell or inside the notebook. So that was an intermediate step that I came through. It's still very, very nice, but it doesn't allow you to save things. It's just like running a session in MATLAB. When it's gone, and you don't remember what you had in there unless you do something to save your command window. But it still can be nice for short little calculations. At any rate, that's a little bit of the history. And if you end up using this in your work environment, you'll find that there's people that locked into different points on the timeline, and not everybody gravitates towards the newest technologies. You're going to experience this through your entire career. I don't know what you think about that, but I've been a person that always wants to learn new stuff and stay current. They tell you that here at UCCS, or most of us faculty talk about that. And our accreditation board definitely wants you to remain in continuing education once you graduate, because otherwise you can be left behind and be stale and not as valuable to your employer if you stay current with different technologies. I'm just going to close that terminal window. These are two PowerShell windows. This one should look familiar. This is started from Julia, and this is how I started my Jupyter Lab, right? This is all the stuff that happened when I launched that up in here. And this one is me running a Pluto notebook. So I launched this one from the Julia prompt again, but I imported Pluto, and then I did pluto.run, and then it brought that up. And that's the next thing I want to talk about very briefly, is how yesterday I decided to post up all the numeric solutions that I did for the homework set number 1, and were done in Jupyter Labs notebook. I decided to also go ahead and just reproduce them under the Pluto notebook, because I talk about the Pluto notebook here in this original document. Remember, the first thing is you cruise down through here, you install Julia packages, and then I had you test Pluto. So you did these statements, and then this pops up in your web browser. Has anybody tried it? I'm just curious, just to see if it comes up in your system. Rather than doing iJulia and then the iJulia command to launch Jupyter Lab, if you were to just follow these steps, when you first get Julia up and running, you would import Pluto, which is another package. Why is it called Pluto? The guy that invented this over in Germany and taught a class through MIT the last year or so, he wanted to be different. So Jupyter is like a planet, right? If it's spelled properly. Remember, Jupiter is contraction of some other letters, but he decided to call it Pluto. It makes sense, right? Just crazy names for things. So pluto.run, and then this thing launches up and it gives you some things in your terminal, but then you see this. So why did I do that? Well, two of you had problems getting your PDFs put together from computed stuff and handwritten. The rest of you did okay. I mean, I filed everything. I looked at some things and worked with it. It's been sitting there in my cloud space where I'm going to grade it on my tablet, but I have not started on that yet. But two of you weren't able to or didn't want to take the time to figure out how to merge documents. It was very easy. The stuff that you guys, two of you sent me, I was able to just take the markdown file and just process it through in VS Code and then merge it together. Remember how I talked about that last week? And others of you did that, right? I'm guessing you did that, but I haven't checked everybody's paper to see what they did. But at any rate, another avenue is to just start a Pluto session. And so I posted that up on the website. What I did is right underneath problem set solutions, I added a zip file of how I could have used the Pluto notebook and then the PDF version of it, which is inside this zip package, to cut apart individual pages that would be for problem 1, problem 6, whatever, and create individual PDFs. So the way that works, I just want to show you briefly how Pluto works. It's a notebook unto itself. It runs in the web browser. It's a little bit different. It takes a considerably different approach to some of the things that it does. You can have GUI controls in it, so I've loaded a package called Pluto UI, and you can also have a command to generate a table of contents, which is kind of nice because you can navigate around your notebook with a table of contents that's right in there, and that gets reproduced into your PDF when it renders that out. And when you go to make a PDF, all you have to do is click up here and say, what do I want to do? And I just click static PDF, and it's going to process that notebook file, and then you can see there it is, and I can just check it, I can print it, I can save it to PDF, which is what I normally do. And it's just another avenue, and I know it'll go down in history, but I'm going to be out of here. Why did he do so much stuff? Why did he throw so much stuff out? Well, I just feel like this is one of my experiments for my last semester, to just throw more stuff out there and grab onto it if you want to. You don't have to, but it's out there because you're going to be, these are things you're going to do, and these are things I'm going to be doing in my work too. I'm actually using it more, mostly for the speed advantage, but just sort of explore what's coming along. So you can close that down. Unfortunately, to open up a new Pluto notebook, once you've got one opened up, you have to right-click over the Pluto icon, and then you can say Open Link, and then it's going to bring you back to where you can start navigating from here down to folders where you might find a notebook. And there are sample notebooks too. They include, in here there's some sample notebooks that are included. One of them is using the UI stuff and other such things. But what can you do with Pluto that's different, and how is it easier? The back end, it's definitely easier, but you do have to, if you want to put in a page break, let's say, you put in this cell, and it's just a cell for putting in a page break. If you don't want to have that cell be active, you can just disable it, which, you know, I've done that before too. You can delete it, but and then you can also hide cells. So where you see the little I next to it, you can hide and unhide things. So if I wanted to hide all the code associated with creating this plot, I would just go up here and it would be hidden. And anything you produce for me, I don't want you to hide the code because I'm grading on what I see for code. But if you wanted to create an output as a report or a presentation or something from a PDF, hiding things would be perfectly okay. Here I used a widget. So this is a markdown cell, but it starts with MD rather than a special cell like you have in Jupyter Lab. And I'm bringing in a slider control that is coming in from Pluto UI package, and the examples show you how that's done. I've also got right here, let's see, an example of how things get hidden in here too. Like here, ingredients is something that I use to import my custom packages, but I'm hiding that code because I feel like it's boilerplate. I just don't want to see it. And Pluto is very, I guess the term for Python, when you say you're following the practices of Python, you call it being Pythonic. Has anybody ever heard that? So for Julia, they call it Julian or something like that. I don't know. They have to have a similar term though, right? It's just community stuff. But at any rate, when it sees the doc string at the top of the function, which is the way Julia works, Python has the doc string underneath the function declaration. It automatically incorporates that and brings that up to the top. So if you hide that cell, you can see that I've got a function that I created, and that's its simple top-level doc string right in this cell right here, which is kind of like I've written some functions. Now I can just see what they are, and they're in my notebook for general usage. So everything else here is the same. I'm importing from Python the Signals and Systems module. I'm imported, well, eventually I used DSP tools got imported. Let's see, where did I do that? I may have hidden it. The problem is when you hide stuff, you can't necessarily find it again. Oh, never mind. I imported it right here. So I imported DSP tools, which is a Julia module that I've been writing. So now what I've done with this little cell here, I've just got a variable called N0, which is in Julia, and it's bound to this slider control. And you can see N0 appears right down here. I'm using it to set the delay of this delta function. So now if I want to use my slider to just animate, this is a very simple animation, but it's just how you can make things interactive so you can just see something happening. I found it to be very useful in my sabbatical job because I made dashboards out of it, and when I collected lots of data from a C++ program I was working on, it was live data that was captured from a software-defined radio. I could use the various sliders and things to pan through the data and look for the instance of something in frames of data. So I made a dashboard out of it, which to me was very nice, and it was very useful when I went into meetings and wanted to say, hey, there's something going on during this interval of the capture. Look what we're seeing right now. Question?
Could you make it vary by non-integer?
Yeah, definitely. You know, all you'd have to do is put, just like in MATLAB, you'd put a colon in there. But I can't let this function down here, this is an integer argument to this function, and I'm subtracting an integer. If I make it be a float, it's going to get upset. Want to see what it'll do? Let's just do it. Because as soon as I put, say, 1.0 in there, it's going to now cast that to a float. And let's just see what it does. Okay, it's still, well, I guess it's still working the way I wrote my Python function for d-impulse, but it's definitely now a float.
Python might be forgiving enough.
Yeah, that's what I'm getting at. Julia is not as forgiving in that regard. So run that cell again. Another thing about Pluto is that all your variables have to be unique because the notebook is now what's called reactive. So if I change a variable in this cell and it's used again in a cell later, it says, oh, he's changing some parameters, I'll replot everything, recalculate everything. So it doesn't allow you to reuse, redeclare variables within the notebook, and it gets angry about that. It lets you know that immediately. It'll say, variable's been declared a second time. You can't do that. So down in here, where I wanted to create a plot, notice I started using some things for my index called NX problem 2, NH problem 2, X2, all of those things to make sure that I wouldn't have a problem with things. So for example, down here, if I add another cell above here, you can see A has been declared as 0.8 and it's reflected in this. If I just say A see what it's saying? It's saying multiple definitions for A. You can't do that. So it gets angry about that. But on the other hand, if I was to change A right in here, let me just get rid of that cell, so I'll go delete it. If I go right here and I say let A equal 0.6 and just rerun the cell, that has changed. It's just reacted in that fashion. So nuances, it takes some getting used to. If you're not totally fixed on one idea, though, you'll probably be more open to the idea that I can accept that. It just means that all the way through here, and that's why I decided to give this to you, I ended up putting underscores and encoding variables to make sure I was never going to create a problem. Another thing Pluto insists upon is if you're going to have more than one line of code in a cell, you have to wrap it with a begin and an end statement. And if you try to put two lines in, it'll flash up a message and it'll say, you need to start this with a begin and end it with an end. So it kind of informs you of things like that. And of course you can have LaTeX code equations in here, which is what's generating that right there. So that's about all I want to say about that. It's just something that's out there. I don't expect you to jump into it like crazy unless you want to. I'm just sort of informing you and letting you see what's out there. It's very, very new. Its version is 0.19 or something like that. So that lets you know that it's not definitely not over 1.0. And I don't know if that means anything to you in software, because in open source software, people count their versions differently. Some people wait to develop a package for a really long time before it finally reaches the 1.0 mark. And 1.0 is kind of like, now it's real. That's in my way of thinking, but a lot of people will stay point something for a very long time and then finally jump up to the big 1.0 release, which it's just different. I mean, in commercial software, you wouldn't think of using a software release that you're paying good money for that's less than 1.0. Is that true? Is that the way you feel about things? Or you wouldn't buy a 0.5 laptop version iteration in terms of prototypes and so on. Another thing that I did here is this morning I posted the hints for set number 2. So I've already got that out here. There's a lot of challenging problems to work in problem set number 2. So I'm going to get started on trying to give some information on some of them. We have to make good, cover some ground before I can even start reflecting on any of the homework problems, because the very first homework problem uses a whole bunch of stuff. So we have to get through more things. So one of the things we have to do is get through classical solution of linear constant coefficient difference equations. Talked about this briefly last time. If you want to take an LCCDE, and remember, we just back up to our fundamental definition, and that's this thing right here. Guess I should clear all my clutter away from last time. And it's just a way of representing an output in terms of past and present inputs and past outputs. And the way this one is rearranged, this difference equation is set up fundamentally, it says a linear combination of past and present outputs is equal to a linear combination of past and present inputs. So it's definitely thinking causality. You can run a difference equation backwards, but in almost all homework problems in the book, everything is running in forward time. But you could recurse something backwards. So the idea is you will set up a recursion, and I think in an example that we're going to get to pretty soon, I take that difference equation. I'm just going to spin ahead to that for a second. And here is just a rewrite of the difference equation. So I just keep the present value of the output y of n now is written as a linear combination of past values of the output and past and present values of the input. This is the way we think of the difference equation most often in practice. This is the way it's used in real-time code. You know, what do I work on all the time, and what have I been working on the past few days? I'm doing stuff in C++ to implement things, but things with difference equations in them, things where there's coefficients, and this basic model is practiced pretty much all the time. It's what makes DSP what it is. If we didn't have this as our bread and butter algorithm for processing a signal with a filtering type behavior, things just wouldn't be right. I mean, we wouldn't be able to do what we want to do. And of course, this is analogous to, this is so powerful in that if you take all your analog circuit designs that are meant to be linear circuit designs, and you want to process a signal from input to output, you would set up an RLC, an active devices type circuit to get the output from an input. This is the DSP version of that. So this is the replacement for a bunch of circuits on a board with connections, pads with capacitance, resistors, and inductance in tracks, and so on and so forth on the PCB. So this is our abstraction of that, just down into an algorithm that runs on the computer. Does anybody have a reaction to that? I'm just curious. Which do you prefer? I mean, you might, you know, if you look at that and me saying that, you might say, that takes all the fun out of it. I don't have to put things on a board. I don't have to pick components. I don't have to worry about tolerances on the components. You just have to build a little state machine, and you're going to study this in Project 1. You're going to be building and writing an algorithm from scratch to do this, but it will also include initial conditions. We'll see that later, but you still have issues though, because those coefficients aren't going to be infinite precision, so you still have some issues to deal with in that area. And then you have, how do you make this efficient? How do you use memory efficiently? Trust me, I like analog circuits from way back when, but I'm comfortable with this because I can do it all on the computer. I don't have to sit there in the lab and prototype something and see what's going to happen when I put it on the board, and I have parasitics, I have tolerance issues with the components I've chosen. Okay, so back up to where we were so we can get into these examples. So the solution to the difference equation is just like a linear constant coefficient differential equation. You have a homogeneous response, and then you have a particular solution or natural response. You have the particular solution and the homogeneous or natural response. So, or what I say down here, forced response. All terms that kind of come from the language of differential equations. So the homogeneous equation is just taking the difference equation and turning off the input side of the difference equation, and that's what we see right here. When we turn the input back on again, then we're interested in finding the response due to the forcing function x of n. So we're going to back up now and just focus on the homogeneous equation. And just like in differential equations for continuous time systems, we'll assume a homogeneous response that's of a particular form. And in a differential equation, and circuits and systems are in differential equations, Remember that idea, e to the minus at? I'm taking you back into differential equations and probably circuits 2 or something. I don't know where, but we have an assumed form of z to the n in our homogeneous response. So we substitute this homogeneous response, z to the n, into the homogeneous difference equation, and then it becomes what you see right down here. If you factor out z to the little n minus capital N for this nth order system, you have left over what's known as the characteristic polynomial. And it's the roots of the characteristic polynomial which are going to determine an individual value for z. So we'll have roots, have n roots, and label them as z sub I, and they go from 1 to n. And assuming our difference equation has coefficients a0 through a sub n, then we can see that those coefficients form the characteristic polynomial, and then you root that polynomial and you get the modes of the system, or the modes of oscillation. And that's something that you should remember from circuits too, that when you drive a system with an input like a delta or something, you're going to get the characteristic response. You're going to get this impulse response, and it will oscillate or have damped exponentials or damped sinusoid functions. So the roots of the polynomial will lead to either all real roots, complex roots, because we have real coefficients. That will mean that the complex roots will always occur in complex conjugate pairs. A special case would be a filter that has complex coefficients, and that can be talked about, but we're not going to talk about it right now. But understand that there are some cases where you'd have complex coefficient filters, but not that often. So we're just going to assume real coefficients. So just like in linear analog circuits, we have R, L, and C values. We don't talk about negative resistances, negative capacitances, negative inductances. We're going to have real coefficients. If the roots are distinct, then you get a characteristic homogeneous solution that's of this form. And if you're just going to solve for the natural response with no forcing function, what you would do is you would just determine these coefficients from system initial conditions. And this will take you back into circuit theory too, where you had, say, a simple RC circuit. You apply no input, and what does the output do? It's going to decay if there's an initial charge across the capacitor or current through an inductor and so on and so forth. Does that make sense? So what's happening here is all the same things. It's just pure math here. There's no circuit elements involved. There's just coefficients and initial conditions. If you have a root that has multiplicity, and we're not going to see that in these examples here, that will show up in the next chapter when we're using the Z transform to do all these things, which is why I called this the classical solution. This is the classical solution technique. The Z transform technique is the next chapter. The Fourier solution technique is later in this chapter. And I decided many years ago that I would introduce briefly to the classical solution technique, mostly because this book has problems that require you to understand it to some extent, yet the authors of the book did not provide any reading in the book on the subject. Interesting, right? Maybe at MIT or Georgia Tech, people learned about solving different linear constant coefficient difference equations the same semester they took differential equations. I have no idea. I had to dig in myself many years ago and learn some of the foundations so that I could teach it, so that the problems could be worked. I was bullheaded. I didn't want to skip those problems. I said, oh, these problems could be interesting for students to work. But it's definitely been a heartache at times. So you're just going to learn enough to get an appreciation for it. And I'm doing it for that primary reason, because when you apply the Z transform, it's like magic. It just does it. Just like when you learn the Laplace transform, it just does it, and you kind of don't even think, why is this working and how does it work? Because you just take it as a little secret sauce recipe and you do it and you get the answer. This is giving you sort of the back, you know, the flip side of it, what is actually making it tick. So how do we solve, so we talked about the homogeneous equation. Now, how do we solve the non-homogeneous equation and obtain the force response? The classical technique that's talked about when you take differential equations, there's several different methods, but the one that I latched onto when I was learning about this myself a long time ago was the method of undetermined coefficients. Does that ring a bell from differential equations? I'm just curious. You know, things go in one ear and out the other ear, or they fall to the floor, but some things are retained in your brain, and I'm just curious if that, does that kind of jog your memory? Like, I sort of remember seeing that. I mean, like, what did they do in circuits when you had to solve it with differential equations? You didn't start using the Laplace transform, right? You had to solve differential equations initially, and then in differential equations from math, I know you do these things too. So method of undetermined coefficients is really pretty straightforward. You guess a particular solution, but the guessing is not wild guessing or you know, just pulling something out of thin air. The guessing is that if you're driving a system with a particular forcing function, you're going to see that show up in the output. So that's what this comment here is. Typically, the force response is going to have the same form as x of n. So if you're driving a system with a cosine wave, you expect to see a cosine wave coming through to the output. It'll have some amplitude change, it'll have some phase shift, but that's the way that would work. If you're driving the input with a constant, and in all of these examples, we're assuming u of n is implied. I mean, we're starting at n is equal to 0. So if you drive it with a constant, that's like looking after the step response. We're going to drive it with a u of n. What's the output particular solution going to contain? It's going to be of the form b u of n. And then there's going to be some other transient part along with that, but just mentally thinking, if we're going to get anything out of a system when we drive it with a step, what does that system have to have in terms of its responses? It has to have a DC, a non-zero gain, in order to support a constant going in and producing a constant coming out. So, and we're going to see here shortly that B will be A times the DC gain of the system, because that's just logical. Now, does engineering typically not defy logic? Not usually. That's one of the things that you become so accustomed to and you get picked on outside of the engineering community is, you're so logical. But that's the way you're being taught to think to solve problems, right? Have you ever been picked on for that, by the way? Or you're sitting with a bunch of non-engineers and you do that and you say, well, it's obvious. And they say, you must be an engineer because you're just, you know, you're thinking very logically. And we do get into trouble in life with thinking logically too much, because it will irritate other people, or it's just, you have to be tactful, right? So at any rate, these are some examples. We're mostly going to hang out right here, or we're going to take the special case of delta of n, which is a special case which doesn't involve a particular solution at all. So, and we'll see an example of that. So the first example I'm going to take is the first order difference equation, which says y of n is a times y of n minus 1 plus x of n. So this is Remember from last week, this is like the banking difference equation. X of n is like a new deposit into the savings account. A is your interest compounding factor, and then Y is the current value in your account. The banking account, though, idea, the savings account idea is good to get your memory churned up, but a savings account is not considered to be a stable system unless we're in a recession or a really hard time, right? Where you're not going to get any interest, your money's going to, well, the money never goes away. A is never negative, but it could be in an investment, right, where you put money in and then it goes away. But from a system standpoint, we don't want the output to become unbounded for a bounded input. Like just putting a deposit in a bank account should eventually mean that it's going to grow and grow and grow and grow. That's not the type of system we want to have, but if you're investing your money, you do want to have that. And right now our economy, I saw the news headline that we had a really bad day on Tuesday, right? My wife and I have a lot of investments or retirement monies and things, and in the last quarter, one of our big accounts lost $30,000. It just, bang, it's gone. I always look at it sort of philosophical, and I'm saying that there's only so much conservation of money. Now that assumes we're not printing money, but if you had it in your account and then it's gone, where did it go to? It's like the tide comes in and goes out, so it got washed out to sea again and somebody else got it. I mean, I try to think that way because it is frustrating, but it can happen though, because it's like conservation of something. I'm not an economist though, although I did have to take 2 econ courses, micro and macro, and some of you have taken those courses, haven't you? Micro econ or macro economics?
I'm taking micro right now.
Okay. Do you like it?
Yes.
Okay. So we can also add into this solution is an auxiliary or initial condition. What is the state of the output when we start the system? Usually we're going to start at rest, but it could be a control system that started up, and the initial condition is the initial velocity of the vehicle, let's say. When the cruise control is engaged to regulate your speed, it took a reading from your speedometer and put that into this algorithm, and now it's using that as a starting point for regulating your speed and trying to keep it constant under windage and up and down hills and so on. Everybody's used a cruise control, right, on a car? Do you like them or you don't, or not like them? I do, my wife doesn't. Add in radar, which I now have, and I talked about that the other day. That makes things a little bit scarier because then it's going to slow you down or possibly hit the brakes for you when, like I told you, the example where I didn't have any obstacle, but it got confused. Some of you may work in automotive and you might work in radar systems though. Okay, so what's the homogeneous equation? We shut off the input, so the homogeneous equation is just this piece right here. We're going to assume a solution of the form z to the n, so we plug that into that homogeneous equation. And if we just look at this guy, factoring out z to the n in this case, we can see that there's one root, and that root is z1 equals a. So not really too surprising, but it's going to be in terms of the coefficients of the system. So now we can just say the homogeneous response is an undetermined coefficient a1 times a to the n. And remember implicitly, pen just died on me. There's a u of n sitting out there, so it starts at n is equal to 0. So now we move over because we could solve for A1 if we were solving for the homogeneous response, but because we're also going to be solving with a forcing function, we need to let that hang for the time being and go over and investigate the particular solution. So our particular solution should be of the form b times u of n, because the driving function over here is that guy, k times u of n. So k is the size of the step. And b is just an undetermined coefficient or scale factor. Remember, I said it's going to be related to the DC gain of the system. But we haven't talked about frequency response yet, so you don't know what DC gain is going to actually be. But we're going to see that a little bit later today. Right? If you have a frequency response, we can set the frequency equal to 0. And what's that going to be? The DC gain, right? Okay, so we substitute the assumed solution b u of n into the non-homogeneous equation. So we're just going to replace, for every place we have y, we're going to put b times u of n, or b times u of n minus 1, whichever is required. And then we're going to have the forcing function on the right, ku of n. And now this is going to seem a little bit on the funky side. This is the exact words, pretty much the exact words from the books I was reading when I developed this. To solve for b, we evaluate this difference equation. This is a mathematics term when none of the terms vanish. Mathematicians like to use words like that, right? Vanish sounds like what? A magician, right? Something will vanish right before your eyes. But you could be more plain English and say where none of the terms become 0. So we have to start for n greater than or equal to 1 to make sure that the u of n minus 1 is actually turned on. So they're all activated in this difference equation. So we get down here, b minus a times b is equal to k, and then we can find what that undetermined coefficient is, b. So I'm just going to mark this for later. I'll come back to that later, but that must be the DC gain of the system. So a step comes barreling through the system, and it shows up at the output with a gain factor of 1 over 1 minus a. So now we return back to the total solution. We have the homogeneous solution with an undetermined coefficient a1. And then we have our particular solution, which is totally resolved. We have it in an acceptable form, k over 1 minus a for n greater than or equal to 0. Now we have to solve for a1. And what we can do to solve for that, or what we have to do, is use initial conditions. We have to look at what is going on in our system namely initial conditions. And there's only one state in this system. Going back to this difference equation, when we start the difference equation up at n is equal to 0, we're going to be needing to have y of minus 1. That's going to be our initial condition for this first order system. We'll need to decide, is it starting from rest, which would be 0, or does it have a value stored in it, like in a control system application? And I guess, just for my added understanding, some of you are probably taking controls this semester, right? How many? Just one? Nobody else? Who else is taking controls this semester? Because there's a lot of parallels between control systems and signals and systems. Signals and systems is the foundation, and controls, DSP, and communications theory sit on top of it. So I don't know, because I haven't asked. Is Dr. Platt teaching it or Dr. Trimboli teaching it? Okay. They tend to alternate back and forth. I know Dr. Platt's teaching Kalman filtering now, which is, I've got one student, graduate student in there who's finishing this semester. That's a very good class. Okay, so down here we go with solving for y of 0, and we go up to the original form right here. So we plug in n is equal to 0, and we get that. We get a1 plus k over 1 minus a. And then we go back to our original difference equation. I'm not going to try to draw the arrow, but I'm just going to say it's coming from the original difference equation. Set n equal to 0, and then we immediately see we need y of minus 1, and we can plug that in. Y of minus 1 was, in the problem statement, was given as c, some constant c. So we make those substitutions now into the equation. We have a times c, and then we have k, and then I can spin things around. What I'm doing is I'm setting these things equal. See if this will get right. Pen reset again. So I'm setting those two quantities equal, and that's what I've done here, and then I'm solving for a1. So I kind of skipped a little algebra step there. I just said a1 is going to be this piece here, and then I brought this down with the minus sign, and then did the simplification, and finally end up with a1 is c times a minus ka over 1 minus a. And when you rewrite it, the total solution now looks like this. We actually have seen something kind of similar to this with that convolution sum equation we did last time. Remember where we worked it in the 3 pieces? We got something pretty similar to that. That was a little bit different because it was a pulse rather than just a step. But if you look at the special case, well, if you look at the full equation in blue there, you can kick back a little bit and you can say, what is this? It's a first order difference equation, and first term there is the transient response. It's the portion that's going to die away as n goes to infinity. So in controls, they call that the zero input response. We're not giving the system any excitation, which is coming through that amplitude k. We're just seeing the initial condition decaying as time goes forward. Does that make sense? Zero input response. And what remains then is the let's see, I'm forgetting my terms now. Zero input. I think I wrote it down below here, but I'm not remembering for sure. I'm not going to try to remember it right now. I'm just going to keep moving. But that's the forced response all summed up. It's the steady state portion, and it's the transient portion rolled up inside of itself. If you look at that, you can kind of see that that's the steady state part that we got from the technique that I described up here. My brain is drawing a blank again. Method of undetermined coefficients. So that's the steady state part. And then the excitation of the input kicks off a transient in there. that part right there. And that portion decays as n goes to infinity, assuming, of course, magnitude of A is less than 1, and this is the condition for stability of this difference equation. So to verify that, we can go through what I discussed for one of the homework problems, and that is just a recursion, where you start taking the difference equation and start cranking it from n is equal to 0 on forward in time, and you get these equations I've written down, or these results I've written down here, and then eventually you see the pattern coming out. This pattern down here generalizes to this, and then this is a finite geometric series that you're going to get at time step n. You can sum that up. Unfortunately, this technique of doing it brute force like this really only, on paper, really only works for first and maybe second order systems where you can unravel the responses as geometric series. Of course, we know that we can use tools like Python and Julia or MATLAB to just crank a difference equation. We have lfilter in Python, the function that I put together called lccde in Julia, and in MATLAB it's called filter. So we always have that available. One little sanity check here that the book includes, and I want to just briefly talk about. There's some observations. This is an LCCDE, first order. In general, the system is not linear because we see that when k is equal to 0, the output is not 0, assuming there's a non-zero initial condition, and that will violate linearity right off the bat. And the system's not time invariant, again, because there's this exponential decay due to the initial condition, which is violating time invariance. But if the system is initially at rest, then the system will indeed be linear, time invariant, and also causal. I'm just putting that up there because we talked about linear time invariant systems, linear constant coefficient difference equations. In steady state, things are linear as we expect, but there is a transient, and if we have non-zero initial conditions, that kind of violates that, but we don't worry about that. We understand what's going on there when we do that. Any questions on that before I start a second example? This will be a second order, so it's a little bit more work. These are the types of things you're doing in the homework, though, and I refer to these in the hints pages quite a bit, actually. Let's just go over and get that ready. So I start referring to examples 2.9 and 2.10 in the notes. And later on, when we get to the frequency domain late today, example 2.22 will be useful. So 2.11, though, is a second order system. And let me just make sure I'm tracking. Yeah, to work problem 1, this 2.11 example is kind of a foundation for that, unless you want to do it in the Fourier domain by Fourier transforming and then inverse Fourier transforming to get the impulse response. And that's, I guess I mentioned that in here. You can work backwards to get part B if you want to work in the Fourier domain. At any rate, I want to at least show you a second order system example, how the classical solution technique works and how in particular you can go after the impulse response straight away There's no method of undetermined coefficients because the delta function is a special type of forcing function that gets managed in the solution all at once. So here we have a second order system. So we have two delays on the output, and that's what makes it second order. And then we have a delta arriving at two different times, at n is equal to 0 and at n is equal to 1. So we can just rearrange the difference equation to solve for the output from the input. This form will be useful later. But initially, we want to go with a homogeneous response, so we're just going to shut this off and get the characteristic equation so we can set up the general solution. So we have the homogeneous equation that's second order, make the substitution, and we get a polynomial z squared minus 3z minus 4 equals 0. And the roots of that are, let's see, why didn't I write the roots down here? I'm looking at it. I don't see them written down though. Why didn't I do that? They're minus 1 and 4. I guess I thought it was so easy that I didn't need to do it. Okay. Curious about how to do that. Quadratic equation is probably the safest way to make sure you get there. So 1 minus 3 and minus 4. So I'm just going to jump into here and put in a blank cell, and I'm just going to go so there they are, 4 and minus 1. I mean, yeah, quadratic equation will do it for you, but it doesn't hurt to just check on the computer quickly like that too. I thought for sure it was in here. I guess they're right there. So that's the general homogeneous solution. And when we go ahead and solve the equation, I've got n greater than or equal to 2 in here, and that's because if we're solving like we did before, if we're considering how does that homogeneous equation actually arrive in our solution when we're deriving it with deltas, that's going to occur when n is greater than or equal to 2 because we know that the input will be shut off at that point. That's the only reason why I put that in there. This is just to denote where the input's already off. So now how are we going to solve the non-homogeneous equation? We're going to just plug values into the original difference equation for 0 and 1, and then we'll be able to activate the the difference equation will be activated by the deltas accordingly at 0 and 1, and then we can force out the solution. So if we go up to I figure out how to make this clear enough. Go up to our assumed solution and plug in n is equal to 0. We're going to get a1 plus a2. And then here, from the LCCDE right up here, I'm going to plug in n is equal to 0, and we're doing an impulse response, so the initial conditions are by definition 0, right? That's the definition of an impulse response. So that term is gone, that term is gone, that term is active, right? At n is equal to 0, that is on, that term is off. So that's where the 1 comes from. And then I do the same thing at n is equal to, n is equal to 1, and from the assumed form of the response, I have minus a1 when n is equal to 1, and I have 4 times a2 when n is equal to 1 in the second term. And then to get the go up to the difference equation, I plug in n is equal to 1, and I have 3 times y at 0, and I have 4 times y at minus 1 plus 2, because that delta of n minus 1 is 1 when n is equal to 1. So I have to write that down. And what I'm doing, I'm kind of combining things, but I get 3 because that's 3 times y at 0, which I found in the previous step was 1. The second term there is 0, third term is 0, the fourth term is just 2. So 3 plus 2 is 5, and then I have minus a1 plus 4a2. And from those two equations, I solve for the two unknowns and get the coefficients, minus 1/5 and 6/5. And that then gives you the impulse response. Now, one of the things you notice about this impulse response is this is not a stable system, because the 4 to the n term is just blowing up. It's just a sample problem. I think it's one that appears in the book, or I found somewhere. It takes off like a rocket, though, and flies away. In terms of responses, I think I actually have it. Yeah, I run it through the L filter function right down in here. This is the sample notebook that I'm going to paste up there for 2022, and see what it's doing after I simulate for a little while. It starts out really small, but by the time I get out to 50, this thing's climbed up to over 1e29. So it's blowing up on you. So this plot is kind of misleading, but it's just because the difference equation is blowing up. And here I put in both the analytical solution, and I drove the difference equation with a delta function. Or maybe come back and look at that a little bit later, but I just did a quick check on it, a hand calculation and a computer calculation of this difference equation. If m happened to be equal to n in the general case, then we'd also have to worry about adding in the impulse response, we'd have to add in an additional delta function term. And what do I mean by m equals n? M was the order of the number of delay terms you have on the input and the output. So the system order is determined by the number of delay terms on the output, and that's 2 in this case. The order on the difference equation for the input terms is only 1. So if we had added another term in there, then we'd have to add an additional term in the solution. So I took an example in here. If this is a first order on the input side and then m is equal to 1, then in solving the impulse response for this difference equation, we'd also have to add in that term right there. That's just required. It's just a rule for solving by the classical technique what do you have to do if m is equal to n. When you plug that in, you do get coefficients, and this one I solved out very quickly as 2u of n minus delta of n, and solve that through a recursion. I get the exact same answer. I get first term is 1, and then it's 2 from then on, because this delta goes away. It only impacts n is equal to 0, and then we're left with 2 for the rest rest of all time. Is this system stable? It's only marginally stable because if we take the absolute sum of h of n, it's going to go off to infinity, right? Because it has a step in it. So I don't know if anybody has any questions right now, but I can stop or I can move on. We're going to go into the frequency response here shortly. I'd like to do that before break time, but we've got plenty of time. Does anybody have any questions yet? And I know when you start solving the difference equations, you might, well, you're going to be looking at these examples in here and trying to make heads or tails out of things. Like, for example, I'll just go off-roading briefly here. Okay, I think that's the top of page 1 of 10 white pages that I just created. So in this problem, they ask you a number of questions. This difference equation is got m is equal to 2, so you have to actually have to add in an additional term if you want to get the impulse response. But let me just see. Trying to remember what they have you do in here. No, never mind. I'm getting this problem confused with another one. This one is not. This one's not too bad. It's the next problem that's the harder one. This one, they just ask you to find the frequency response, and then the second part switches gears to another problem. It says find the frequency, find a difference equation. So that involves an inverse Fourier transform. So 2,6 is really all in using Fourier transform ideas. So the problem I was thinking of, and I want to talk about that, but we're not there yet, so I picked the wrong problem to start with. Let's just write this down for clarity again. This is 2, m is equal to 1. So although all you're working is part A, there's 3 parts to part A. Part A says find the impulse response, find the frequency response, and find the step response. So Frequency response will be a technique that we'll learn about shortly. It's actually very easy. It's taking the Fourier transform of both sides of the difference equation and then forming the ratio of y of e to the j omega, the frequency response, the spectrum of the output divided by the spectrum of the input, x of e to the j omega. Impulse response, you can inverse Fourier transform the frequency response, or you can do the classical solution technique, which is going to be the most fun. I mean, in terms of learning about getting practice at solving difference equations. The Fourier technique, you have to do a little partial fraction expansion, which isn't really talked about in this chapter, so maybe this is the better approach, but you're going to be considering these two inputs. You're going to get the impulse response, you'll just drive it with a delta, and then you'll get characteristic polynomial, coefficients, A1 and A2, method of undetermined well, then you'll just integrate into that delta of n, and you'll eventually solve for A1 and A2. When you move on to the step response, though, then you'll be putting in, this is your forcing function, you'll be solving the method of using undetermined coefficients to get the force response. It'll be something like b times u of n, and then you'll solve for that, all using the classical solution technique. But I also point out, and I think that's in the hints, but I'm just going to point that out right now, just as a reminder. If you don't want to back up and solve the step response from classical solution techniques, you can also start from a different approach, and this is a linear time invariant systems property that if you already have the impulse response, which is what this is going to allow you to get, and you want to get the step response, the ys means the step response, you can accumulate, and this will be a causal system, so you're going to accumulate from k is equal to 0 to n, and that's just using a fundamental principle of linear time invariant systems. If you integrate, you got a question?
Yes, sir. I'm just here to grab that logger off the wall over there in the corner by the clock.
Okay.
Is that okay?
Yeah.
Thank you, sir.
As long as it doesn't scream loudly when you do that.
Oh, no, it's not going to be nothing.
Because we'll plug our ears if we're going to get a screech or something. I remember reading about them, though. They were in the email last week, right?
Yes, sir.
You guys don't know what that is, but it's some logging device for probably saving money, right?
Yes, sir. It's for the energy project they're doing.
Yeah. There's no hope. I'm just saying that we have to give up everything if we don't want to use any energy, right? Go backpacking and you understand better about energy usage, right? If you don't want to bring your backpacking stove, you're not going to be able to cook a meal. You can start a fire, though. You can burn some wood, probably. Okay, so what I was saying, though, is that remember about linear time invariant systems. Remember how in discrete time systems, the integral is equivalent to accumulating, and that's what's going on right here. And in systems theory, if you want to get the step response and the impulse response are related to each other, because we know that if we take the first backwards difference of a step, we get a delta. So if we accumulate a delta, we get a step. So that's our input. Those are these two inputs. So if this gives us the step response, it says if we accumulate the impulse response, we should get the step response. So it's just sort of, since it's linear, we can apply these operations before or after. So here, if we apply it to the impulse response, we're converting it after we've gotten the impulse response. This is the better practice for just working with the difference equations and solving with method of undetermined coefficients. It'll be satisfying to parallel this with the examples I have in the notes. If you choose to go that accumulator route, then you're going to get practice at summing geometric series and just seeing how that comes into play. They both have, value in terms of practicing. And when you take and look at things differently, you might, well, you're going to learn things. I mean, I'm just looking at my solutions, and you'll get used to looking at my solutions as being kind of fat because I do a lot of different things. I try to take different approaches, and I try to sometimes do more than what the problem asks for, just because I want you to see that if you've been curious about anything. I don't want you to ever think that being a minimalist is the only way to fly. I mean, sometimes you have to just dump some extra time because you learn a whole lot more. But I realize you're constrained by your jobs and other courses. So I have gone off the deep end frequently on these problems because I've wanted to explore other approaches, especially because I'm the one that gets asked the questions, right? Here I am, I'm stuck. And I could say back up and come in this way, or I could say you can get it from here, but you just have to power harder to drive through that. It's like trying to go through a big snowdrift. Do you get a running start at it to get enough energy to break your way through? Okay, before we take the break now, I'm going to talk about frequency response. I do introduce and talk more about L-filter in here. I've demoed it. I've demoed the LCCDE function I created for Julia. L-filter has also got the ability to put in initial conditions. I'm not really going to dwell on that right now, but I did do an example down here where I used repeated an earlier example in the notes where we were driving a rectangular pulse or convolving it with a first order difference equation. We get this pulse response, and then I took it a step further, made it a second order system. It was underdamped, and then here I took it and applied an initial condition. So in this case, we were able to see what the initial condition is doing, and because I'm solving this with a causal process in mind, what I did is I played a game where the input started at 0 with an initial state, but I made it look like the system was settling from its initial condition and the input was applied at 0. I actually applied the input at 5, I think is what I did in this example. I don't see the code for it though. So there's different games you can play, and depending upon how much practice you got using LCCDE or L-filter in the last problem, set number 1, this is just more of the same. And I've only looked at some of the papers in that last problem, and I know people got it right. It's just, was that a good experience just to do simulation, just to crank an output from an input? Because I provided the full solution, the hand solution too, but that was not required. I just wanted you to be like a technician, and you're going to sit there in the lab, I'm going to apply an input and see what I get. And that's what you should have done. I'll maybe jump over to the notebook and do some things after the break, but right now I want to get this idea going. Frequency domain representation. The way we get at the frequency response is initially considering applying a complex sinusoid that starts back at -infinity. This is fundamentally the same idea that you would see in continuous time linear systems, where you're going to go after the sinusoidal response. Here we're just starting with a complex sinusoid, just let's get it over with. Let's not mess around with sine or cosine. Let's just put in a complex sinusoid, but started at minus infinity, so that when we're looking at essentially time 0, the system is, as long as it's stable, it's fully settled and it's in steady state. So what we get out of that fundamentally is we want to convolve the input with our impulse response. So we're going to do the convolution sum right here, and that means we're going to just drop in h of k and x of n minus k. And then notice that e to the j omega n factors out of that, and what we've got left over is this sum, and that sum is the frequency response, because it's saying that since we're starting at minus infinity with the input, we're already up at steady state, so we sum that doubly infinite sum, and that is going to give us the frequency response. And this, in the book, they like to call it as the eigenfunction property, and this eigenfunction is like an eigenvector in matrix theory. An eigenfunction is a resonant mode that hits one of the modes of the system and produces an eigenvalue related to that. I mean, that, remember, the matrix gets replaced by an eigenvalue when you have the eigenvector computed from the matrix. I'm not trying to go and teach linear algebra, but I'm just saying the eigenfunction is just a generalization of that idea where you're hitting at a resonant point. So the function in parentheses is defined formally now as the frequency response corresponding to a linear constant coefficient, or I mean a LTI system that's been described by its impulse response. The next few pages, we back up again and we say, oh, we're going to define the Fourier transform of a sequence, and we're going to see that the frequency response is just the Fourier transform of the impulse response, a concept that you've seen before for continuous time systems. So the special case of driving with a complex sinusoid starting at n is equal to minus infinity produces an output sequence that is just the input sequence weighted by a complex factor h of e to the j omega. And if this seems confusing, it might be better to just think of omega in that equation as being a constant. It's just, we picked a value of frequency like pi over 3 or something, and we're just going to see what the sequence looks like coming out. So I know what can go through your head when you see that. It's like omega is changing and n is changing. What is going on here? What do I have? It's not intended to be that way. It's just saying that for a particular value of omega, and putting the subscript on there is helpful. Just think of it as a particular value of omega, and we'll get the response to that. Real and imaginary parts, magnitude and phase go along with the frequency response, just like you've seen before. And you can extend this idea to a linear combination of sinusoids going in, so you get a linear combination of sinusoids coming out, all that are picking up the individual magnitude and phase responses at the omega sub k values. I think I'm going to just stop right there. Just before we take the break, though, I'll just say we're going to have MATLAB has this function, Python has this function, and Julia has this function, freq-z. You remember that from MATLAB? So this is a tool that we get to use to calculate frequency responses, and it actually uses, under the hood, the fast Fourier transform. I'm not going to get into explaining that right now, but it does. It's a numerical technique. It will not evaluate the function for all values of omega, but more on that. Let's just take the break right now and come back at about 47, I guess, according to that clock. My watch says 9:31, so that clock is a couple minutes fast. So on your watches, it'll be 9:46. Would be a nice time to be back. We're back from break now. Not everybody's back in the room, but we're going to go on and look at some examples and look at properties and eventually get more stuff covered for the homework problems that you're working on right now. Obviously, we're working our way towards the end of Chapter 2. We'll get close to it, but we won't have everything neatly tidied up. So the next example in here is just taking a very simple system, a delay system, which shows up a lot, either intentional or unintentional. We're going to delay by ND samples. So what is the frequency response of a pure delay system? So just jumping back into the convolution sum, if the input is what we were looking at, e to the j omega n running from minus to plus infinity, we just drop that into the convolution sum formula, and we'd be dropping in only the change of variable. N gets replaced by n sub d. And when we factor that out, we can see the frequency response of a pure delay is e to the minus j omega n sub d. So generally, when you're looking at a pure delay system, don't worry if you came in late, you didn't miss much of anything. I'm just on this first example, but if you're doing the phase plot of the e to the minus j omega n sub d, you just see that the phase has a slope of minus omega times n sub d. And that is called the linear phase, and the fact that it's a negative slope is indicative of a delay. If it was an advance, which would be a non-causal operation, the phase slope would be the opposite, but all causal systems will have this negative slope to it. Signals getting delayed. So in the frequency domain, it's just picking up a linear phase. Alternatively, we could just find the impulse response, and we know that for a pure delay system, we could just go right up here and immediately say if this is delta, that's h. I mean, that's how simple it is with a pure delay system. So the impulse response is delta of n minus nd, and then going up to the equation up here in the blue box, we just drop that in, and we're summing from n is equal to minus and plus infinity, but the only term that's going to evaluate is when n is equal to nd, so that pops out e to the minus j omega nd. So the Fourier transform, as I'm going to call it here soon, is just that single term popping out from the impulse response delta of n minus nd. And the characteristics, like I've already been saying, the magnitude response of a pure delay is 1, and the phase is minus omega times nd. Just as a sanity check, since everybody here is familiar with transmission lines from EMAG 1, 3110, right? the first EMAG class that Dr. Song teaches. I taught it for her back in 2016, actually, when she was on her first sabbatical. I like transmission line theory and microwave circuits. I used to do a lot with that stuff too. But an ideal lossless transmission line is an example of a system that approximates this. It's not a discrete time system, but it has a pure delay of tau d seconds, and it produces a linear phase and a gain of essentially 1 when you normalize it in a, say, a 50 ohm impedance environment at the sending side and the receiving side. If you look at what the frequency response is, it will be 1. If you want to model it more precisely with the source and terminating resistors, it obviously has a attenuation factor of 1/2, but that's just looking at the load and source, the fact that the load is 50 ohms, the source is 50, so half the source voltage is across the load, but that's sort of built into the model of the transmission line. So this is a discrete version of that. It's used in a lot of different applications. Pure delay is in the Hilbert transform front end of a receiver, which I'm not going to talk about that in any example problems in this class, but in the real-time DSP class that I taught last spring, it shows up in there. I had a guy write to me over the weekend about something he's teaching for the DSP online lecture series, which starts on October 3rd or something like that. You pay money to attend these classes, and this guy's been teaching classes on Python, in using Python for signals and systems modeling, using Python for software-defined radio modeling, and he asked me a question about giving an advertisement for my Signals and Systems for Dummies book in his class, saying this is the background I'm going to assume, and he's going to go through a lab experiment of doing a Hilbert transform, which is something that I could talk about in here, but I typically would talk about it in Com Systems 1, or it showed up in real-time DSP. Kylie, you remember we did that in that one demodulator, right? So I'm thinking that's what he's going to do. I'm not going to sign up and pay money to watch his lecture, though. I just sent him some links to my website where there's examples of how to do that. But that includes a pure delay. You need to have 2 branches to make that work. So another piece to the puzzle here is just to go back to something fundamental from signals and systems. What happens if we have a real sinusoid going in? So rather than the e to the j omega n, let's just put in a cosine omega naught n plus phi. What is y of n going to be? And this is a really good question to ask, because as an electrical engineer, you grow up with a hands-on experiment in the lab one day or another where you have a function generator, you have a breadboard, and you put a resistor and a capacitor on it to make an RC low-pass filter, and then you connect the oscilloscope to the output, and what do you see? You see the sinusoid coming through the output, you see it's been phase shifted and amplitude attenuated by, depending upon the frequency. So how does that look in DSP? It'll work the exact same way. So here we have, in order to prove and get a general formula for the case for a real sinusoid, we would use Euler's identity and break the cosine into 2 complex sinusoids. So here I'm going to take, I've already done that here, but I'm just going to remind you what it is. So just use Euler's identity to break apart the cosine, e to the j omega naught n plus e to the minus j omega naught n divided by 2. And that's what I've done here. And then I'm just using the eigenfunction property that we just talked about, and I'm going to multiply times the frequency response at the individual frequencies. So these are the two terms, so I need to take the sinusoid at frequency plus omega naught and multiply it by e to the plus j omega naught, and then for the e to the minus j omega naught term, which is the second one, I need to multiply by, with a minus sign in here. So it's activating the delta. I'm getting ahead of myself. It's activating the frequency response onto the positive frequency sinusoid and the negative frequency complex sinusoid. So in order to get this to a convenient answer, we're going to assume that h of n is real. So we're going to go inside, and this is one of the properties of the Fourier transform, so this is needed to finish this problem. So I'm just going to do the short proof of it right here. How is h of e to the minus j omega naught related to h of e to the j omega? So I go across here, and it looks like I have a typo in here, actually. That should be e to the minus j omega naught n, if I'm just going to follow through with solving for minus omega naught. But then, maybe I don't have a typo. How did I do this? I probably thought this before. I'm going to get myself confused. These notes were written such a long time ago, I thought I got almost all the typos out of them, but maybe I meant to have that. I'm not positive anymore because I'm looking at this. I'm saying, okay, so the next step is I have the minus sign in there, and then I conjugate the whole thing, and then that's going to tell me that fundamentally when I get done, I'm probably just a little bit confused because I'm already starting to get a little bit of brain decay from lecturing for too long. And you have the opposite. You have the brain decay from listening for too long. The bottom line, though, is I'm showing that the responses are conjugate symmetric. So h of e to the minus j omega naught is the same as h conjugate of e to the j omega naught. That's really the bottom line. So I can pull that out. So in this first expression, I can pull it out as the magnitude of h of e to the j omega, and then I can leave the angle inside the argument of the cosine, so that I have either a positive or negative angle depending upon the sign. And in this case, I just put it in as the positive value when I factor that out. Because in Euler's identity, I'm going to be putting in, up in here, I'm going to be putting in angle of h of e to the j omega naught. And when I bring the minus sign in there, then it will show up as the conjugated angle, which would be the minus sign. So I can combine that together into this blue box, which just says the output is the input cosine that picks up the phase shift at the frequency, positive frequency omega naught, and the magnitude response of h of e to the j omega naught is applied to that waveform. Going back to the special case for the ideal delay, we of course see that we're just going to pick up the linear delay, which is a negative phase factor. Let's just do an example, though, since maybe this will help wake me up some more. I could do this in Julia. I could do it in Python. Here's a frequency example. Which language should I demo it to you in, or daydream in? Python or Julia? I'll do either one. It doesn't matter to me. Okay. I know you're going to, most of you are going to be reluctant to want to learn the new language, but you know, I'm just saying you can tinker sometime into the future. So what I'm going to do here is I'll just create a range 0. I'll just go 50. I might adjust this later. I'm going to say x is equal to and I'm going to make this fairly slow. I'm going to make it 1/10. So the frequency here is going to be 2 pi times 0.1 times n. Okay, there's my sinusoid. Now what I'm going to do down here in the next cell, I'm just going to process this through a difference equation, or I could process it through something else. I'm going to go back to our difference equation and all that we've had, and I'm going to take I'm just going to write this as a comment. I could write this in a markdown cell up above here. I wanted to, you know, put in a markdown cell. Okay, so we've seen that difference equation already today, so let's set A equaling 0.8. And then we're going to use, we're going to go ahead and use L filter just because it will make it easier. We're going to say y is equal to signal, and I just hit the tab key just because I'm going to be lazy and get signal out of there, dot. And then remember, this is the entire library of signal, which is a submodule of the big package called SciPy. So L filter, first hit. If I wanted to do initial conditions, I can set them with L filter underscore ZI, but I'm going to do just L filter. Then I'll put my coefficients in 1, and I'm just going to get that because that's the coefficient on here. And then I'm going to rearrange the difference equation to have outputs equaling inputs. So I have a single coefficient B0, and then for my A array, I've got 1, and then when I move sides, move this y of n minus 1 to the other side, it becomes minus A. Then I apply my input, x, that was created up above. Then I'll just replot y now. And the best way to see this, and this is sort of a cheater's way, but sort of abandon the stem and just connect the dots just so you can more clearly see what's going on with the phase. And so what I'm going to do here is I'm just going to do an overlay plot. So I'm going to do plot and if I wanted to be fancy about it, I could also well, do I need to do that? I could plot the dots on top of here too. I don't know, I don't think O is orange, so I don't think that's going to work. I'm just going to go with blue, make sure the colors match. Then we do the same thing down here just for the other one. Blue and red is what I'm going to do. And let's see, I've got an extra. Yeah. Yeah. And what did I do wrong here?
Two dots for the effects. You have a dot after the B.
Yeah, I see that. Okay, and then I could add the grid in here at the bottom. And generally, when I'm using Python, I'll put a semicolon because matplotlib likes to put out this address of the graphic. So if I put grid at the bottom and put a semicolon on it, then I'll suppress that return. But that is phase shifted. And if I lowered the frequency, so suppose I go all the way back up here and I say, I'm going to lower the frequency, make that be 0.02. So something like this. I'll just go down here and replot this. Wait a minute. Maybe we could run through the filter again. But now I need to put in more points. Now we're going to see something else that's happening in here. This is the thing about doing an example like this, is you get to have more fun with code stuff. So I'll do 400 points. That may be overkill, but I'll rerun the filter. I don't really care about that. It's getting too dense to look at all the stem plots. But now we're seeing the transient, which is coming through the output. That's the transient solution coming on through. Remember, we talked about that earlier. So the phase shifting idea is not really going to be active until we get a ways down the line. So we can do an xlim command, and let's just go from 100 to 200 or something, or 300. Okay, so we definitely can see there's phase shift on here. And remember, we're talking about frequency response. I'm not so much interested in the difference equation, although we can see what's going on there. We can see our sinusoidal steady state response model assumed the input started at minus infinity, right? So what did I just do to kind of deal with that? I just moved myself down into where I was in steady state. Is that okay? I mean, I'm just working in present time, and I just move out of ways, and I'm in steady state. So I can see the phase shift, and I should be able to pick up the phase shift at this frequency. But one of the things that we ignored from way back earlier in the lecture, and I'm going to move. I'm just going to move this down here so you can see it better. One of the things that I didn't do with this difference equation, remember, what was the DC gain of this difference equation? And now I'm seeing the math here is messing up. I noticed this morning. So if you're interested in putting in math, oh, I see what's wrong. Some of this notebook has to be fixed. So I'll fix that later. I know what's wrong with that. Never mind, I don't want to say something that doesn't apply right now. But this difference equation, what was the DC gain of this difference equation from earlier this morning? Or what was the gain of? If we want to make this apples to apples comparison, in other words, input versus the output, we might want to make this difference equation different. We might want to scale it by so I might want to put a 1 over 1 minus a onto the input so that it would be unity gain then at DC. So if I do that over here, I would just be putting 1 minus a in there. I'm going to drop down here where I can plot it better though. There, that looks, to me that looks a lot better. I was getting an output that was bigger than the input, and that's because the input, the gain of the system at DC is 1 over 1 minus 0.8, which is 1 over 0.2, which is a gain of 5. So now the idea that we have a low-pass filter and we're putting an input in at a frequency that's, you know, above DC, we're going to see the attenuation idea taking place in here. Let's just take this even one step further. Put this down in this cell so that I can just do that part of it again. I just raised the frequency from 0.02 to 0.08, and you can see now I'm seeing more of the roll-off of action of the filter, whereas if I was to take this down to 0.01, now there's the phase shift is obvious, but you're seeing the gain is almost 1 to 1 because I've adjusted the DC gain of the filter by doing that. Maybe I've done too many things. Maybe I shouldn't have done that, but that was my choice. Any questions on this? I mean, you're seeing gain and phase shift, and I played around a little bit with the DC gain of the filter as well. That filter doesn't show up in this example. I'm just trying to leverage this, though, as a hands-on example. Rather than going into the lab, you're just playing in Jupyter Lab and putting a sinusoid in and testing it here. And we, just another quick note, if you want to turn commenting on and off, Control/ is pretty much a standard editor in almost all integrated development environments. So I'm just holding down Control/ when I'm sitting in that line. All of these have some transient though. That's because we started the filter at 0 initial conditions for this case. Any questions or comments? You could get you could observe the phase shift at this frequency though if you just looked at the zero crossing difference, say right in here, and then took into account how many samples are in one period, and then you could get the phase shift, right? And that should match the phase shift. And if we wanted to get the phase shift, we could use freq z, and that's where we're headed to next. But I don't know if I want to do that right now. I'll do it though. Hit tab again, hit F, FR, there it is, freq z. This is talked about in the notes, but I'm just going to go ahead and load it in. So I'm going to load in this exact set of coefficients that we're using right up here. Then I need to put in a frequency. Rather than having it evaluate at a lot of frequencies, this function though, unfortunately, if I do Shift Tab, it'll tell you how it works. Returns an array W for omega. I don't like to use this function in an automatic mode. I like to be deterministic, so I like to use it in this mode where I'm going to say F is equal to a range. And here I'm just going to give it a couple of values. I'm going to give it 0 and what frequency am I running at right here? I'm running at a normalized frequency of 0.01. And then I'm going to multiply by 2 pi to get it in terms of radians. And then if I go ahead and take a look at the absolute value of h over here, let's see, what did I do wrong here? F, oh, I know what I did wrong, I think. Okay, what I did wrong was in Python, if I just put square brackets up and put numbers separated by commas, I get a list. But if I want to do vector operations, and Julia works the same way, I have to make it an array. So to make it an array, an ND array, which is part of the NumPy package, I have to wrap the list with this function called array. And if I do a shift tab on that, it's a very primitive function. It's telling you it creates an array. So I made it an array, so now I can go ahead and multiply that array by some constants, and that's what it was complaining about, because Python by itself doesn't know how to multiply a list by a constant. It's like, what? Does not compute. But array has got the properties that you can multiply and divide by scalars and add arrays of equal dimensions. So there's that, and then if I wanted to just do a quick print, I'm doing a lot of extra stuff right now. You can do formatted printing. I'm not going to do a formatted print, though. I'm going to print. Angle, what is angle? Well, angle is part of NumPy, and I've imported all of NumPy into this notebook so I don't have to precede it by the library name. So magnitude at DC is now 1. Magnitude at that normalized frequency of 0.01 is 0.96. The angle at DC is 0, and then this is the angle in radians. And of course I could get that in degrees if I wanted to. So minus 13 degrees, so that's how much phase shift we have here at these zero crossings relative to the full period. Does all this stuff make sense? I want you to do anything and everything to make things feel comfortable, so I haven't gone through the use of the tools, but I'm going to be doing that here shortly. So what's the fundamental difference between the discrete time and continuous time is that in the discrete time case, h of e to the j omega is always periodic, and that's because from the get-go in this definition of h of e to the j omega, we have e to the j omega, which is going to have period 2 pi. So we have unlike in the analog continuous time domain, frequency starts at 0 and zooms all the way up to infinity. In the discrete time domain, it's always periodic, and that's related to the underlying sampling nature of our waveforms. And we'll see more of that when we get into sampling theory. So the fundamental interval is 0 to 2 pi or minus pi to plus pi. And you can, this example just shows you what happens if we shift omega by 2 pi. Over here, you'll get a 2 pi n factor, and that is just 1. So that just proves that it's periodic with any integer shifting that you want to do. I'm going to come back to these examples, but because I want to show you where some of the numeric stuff is in here, we'll have Fourier transform of sequences, which is just taking and doing the same operation on the sequence, but way down in here is where I finally get into using Python to do Fourier transform. So here is where I've got freq z laid out in here. And in Julia, I don't have nearly as sophisticated of a setup because the community hasn't built really nice tools, yet they haven't, and I'm trying to change that in my own little way. So in my version over here, if you were to be playing in Julia, you'd have to go to DSP, Tools, and then my library is very small right now, but there is a freq function, and it brings up help for it. This was the help that I wrote for it. It just finds the frequency response in terms of polynomials b and a for a given value of f. So I'm putting in a normalized frequency f rather than omega, very much like I used the function in Python. So we want to get there before we're out of time today, but I'm going to back up and look at a couple of examples, and then I'll get into the Fourier transform as much as I can. So an interesting example is, what about doing something backwards? Suppose we want to design a digital filter based on an analog filter that's an ideal filter. So here we're going to take and look at an analog filter, which is 1 in the passband, 0 otherwise, and then look at the equivalent of that in the discrete time domain. And of course, because anything that's got a frequency response in the discrete time domain is periodic, so pictorially we'll be talking about trying to construct a filter that looks like this, that would repeat every 2 pi. And later on we're going to be seeing that in frequency this will be fs and minus fs. So when we work with sampling theory, pi corresponds to the folding frequency, fs over 2. So that'll come into focus. But this would just be how we can describe mathematically an ideal low-pass filter. When we get into this in another part in the notes here, we'll be doing the inverse Fourier transform of this, and we'll see that it's not so simple to get that design. But you can still write it down mathematically as an ideal low-pass filter in the discrete time domain. Okay, an important filter and an important idea is an impulse response that's a rectangle. What does that look like in the frequency domain? So here we're just going to use the moving average filter as the example, but this is a rectangle in the discrete time domain. It's not centered on 0 because it depends on M1 and M2, but it's something along those lines. So that forms a rectangle, 0 outside that interval. If you want to get the frequency response of this moving average filter now, we can just essentially Fourier transform or use the blue box equation for the frequency response and jump right into it. Our sum is going to run from minus M1 to plus M2, and we're going to be, forgot to put the scale factor in here. That's, again, make sure it's unity gain at DC. But the key to summing this is what? Remember I told you geometric series would show up over and over again. So what is that? It doesn't maybe look exactly like a geometric series, but if you rewrite it as minus j omega to the nth power, it is a geometric series. It's a finite geometric series, once again. We just have the ratio r in the geometric series is now e to the minus j omega, which is a complex number. But it still works, the formula still works, and that's how we get this form down here. And then this is kind of the next step that gets taken in most of the notations, and that is that rather than leaving it in that messy form with the complex exponentials, you can factor it in terms of a sine nx over sine x, and then multiply by a phase shift factor, e to the minus j omega m2 minus m1 over 2. So notice I use the word after considerable or additional. Maybe you'd call it considerable for now, but in the future you're going to say that wasn't bad at all. You'll get used to it. So additional manipulation now, and it's really the real trick to this is taking the difference between the two exponentials there, and from the outset you should be seeing that the ratios there are really two sine waves, because whenever you see an exponential with a positive argument minus an exponential with a negative argument, your brain is supposed to say, oh, that's a sine, right? That's in the form of a sine. There's got to be a 2j under that. And then in the denominator, that doesn't look quite right, but if you factor out an e to the minus j omega over 2, then you will have an e to the plus j omega minus an e to the minus j omega. Sound okay? I mean, in principle, I'm not going through the nitty-gritty, but I'm just saying it's going to be the ratio of two sines, and then there's going to be some extra terms, extra exponentials, so it's not too far-fetched to see that this is what we've got right here. We've got a centering term, which is the e to the minus j omega, that has the m2 and m1, and that's just due to time delay in the system. That's going to cause some linear phase. And then we have the ratio, and this is called pen needs to be started again. In general, this is sometimes referred to as a Diric function. In MATLAB, they called it the Diric function, actually D-I-R-C, D-I-R-I-C. I'm not sure if Python has a name for it or not, but it's similar to a sinc function. So you've got an argument x. In this case, x would be omega over 2, and then you have m times x in the numerator and just x in the denominator. Looks like I used n over here. The letter I choose doesn't matter. But what does matter is that this is related to the sinc function that you've seen before. This sinc function is periodic, whereas the general sinc function just has one main lobe and then ripples off to plus and minus infinity. There's a relationship, though, in that when you alias, and we'll learn more about this in chapter 4, an aliased sinc function is this sine mx over sine x function. So the fact that it's showing up in the discrete time domain where you have the periodic sinc kind of a function is not a surprise. I'm telling that to you because you can believe almost anything right now, right? It's like, tell me what the math means. You know, what is it when you first learn something? You see the math and you say, that's really cool. How am I going to remember that, or what's the significance of it? But then eventually you start realizing that these mathematical things are related to other things that you've already known, and it's there for a reason. It's not totally mysterious. I find that's really comforting. You know, when you learn math concepts and you say, this is really way out there, I can't possibly ever retain this, but then you realize how it's related to something you've already known before. I mean, maybe I'm not coming up with a good example, but this is an example of how a sine x nx function is related. So there's the response of that. It's a periodic sinc function, and it's got linear phase. And the linear phase is because of what's going on in here. And then the sinc function and this alias sinc function both just have sign flips in them. Okay. Can we deal with that in Python and MATLAB and Julia? Because we have the ability to have a sinc function, we can deal with it. And I honestly don't remember, so I'm just going to go check over here. Since I have all of NumPy loaded, and I forgot to say this at the beginning of class, I got sidetracked and never came back in. Newer versions of NumPy and newer versions of Python, I should say, do not support this magic called PyLab inline, which will allow graphics to come into the notebook and allow all the libraries of NumPy and matplotlib.pyplot to be imported, so they're just there, just like you're working in MATLAB, which all of you learned, me included. So with this newest version, they say it's deprecated. So if you've been seeing that warning message, deprecation, that's actually okay. It just lets you know, hey, this is soon going to be gone and I'm never going to be able to use it again in my life because it's going to be out of this version of the software. So the way to get the deprecation warning to go away is to just brute force import all of NumPy with that from statement, and then import all of the submodule of matplotlib, our graphics, which is called pyplot. Import all of that, so then we're kind of back to where we wanted, and then also tell matplotlib with its magic that I want it inline, and inline means the graphics show up in the notebook rather than separate windows that would open up in your on your desktop. So when you get to be a purist, you should just not do these things. You should just import NumPy as NP and probably import matplotlib.pyplot as PLT plot. That's what kind of the community does. But I'm doing all this importing because I want this environment to be very user-friendly in the beginning. So where was I down here? I was just going to see what's available. So sync should be available if I hit a parenthesis and hit a shift tab. There it is. I do not think Duric is in here, but nope. But I can create one using the sync function. I just have to be careful then because I'm going to have aliases going on. But here, in this example right here, you can see I just used freakz to go ahead and evaluate a pulse that is 5 ones long, as if it was a causal moving average filter. I just said, evaluate it for me and do the plot. To see that it is indeed periodic, and I did it in decibels on top of that. See that it's indeed periodic, I could run this out to point 1.0, and then we're seeing first period, the center at 0.5, and then it starts over again and just keeps rolling on, just like the notes showed. Generally, I don't need to plot all of that, but that matches up with this picture here, except the notebook picture is in decibels. I did 20 log base 10, right, of the magnitude. Okay, a couple other things as time is rapidly ticking away. I'm not going to look at that example. I'm going to just briefly review the definitions: Fourier transform, inverse Fourier transform. There's a few more details to the necessary and sufficient conditions for the existence of the Fourier transform, and I'm going to save next time to go over that. That's sort of a practical, sort of a deeper theoretical nature, but these are the forward and inverse transforms. And this is the only integral that shows up in this course, in the discrete time domain, when we want to take the Fourier transform of a sequence and get back to the sequence domain again. We have this integral, which, because this function in here is periodic, this can be over any 2 pi interval. It's shown here running from minus to plus pi. So these are the convergence things I was going to talk about. I'm going to go back and go through this example of the ideal filter again and look at its inverse Fourier transform and see why it's really hard to make one of these. Go through some special cases of Fourier transforms. Frequency, we've already talked about that. Why am I cruising? It's because I just want to get you to a few punchline areas for the homework problems, just to allow you to move on them if you want to get started between now and next Wednesday. So then we have a lot of theorems and symmetry properties and so on. So symmetry properties, the biggest thing is to know that if x of n is real, x of e to the j omega is conjugate symmetric. So x is now the Fourier transform of a sequence, but if it's the Fourier transform of h, the impulse response, then it's the frequency response, but it's in the frequency domain no matter what. So what we have in terms of theorems, we have a lot of standard theorems. More on these later, Parseval's theorem, but this one shows up in the homework problems. It's a very fundamental theorem. It's the convolution theorem. It says convolving in the sequence domain is multiplying in the frequency domain. This should be like, hooray, it's something I'm familiar with, I'm comfortable, I love this one. And I do. It's very useful, and that's why I'm speeding to it right now, because I'm wanting to show you how powerful it is when we go down and look at. There's also a table, and that's a crib sheet that you'll have. Remember, I showed you the crib sheet before. You'll have these theorems. But I want to take this example right here is very similar to the first homework problem and can be utilized in the second homework problem and can be utilized throughout a lot of the other problems. If you have a difference equation description for a system, in other words, you don't have its impulse response yet, right now from earlier today, we know that you can get to the frequency or the impulse response by solving the classical solution technique. If we have just the difference equation and we want to get the impulse response, we can kind of take a roundabout way to get there. Thanks for closing it. We can first go to the frequency domain and then inverse Fourier transform and eventually use the Z transform to get back to the impulse response. So how do we get the frequency response? We just take the difference equation and we have something called the delay theorem, which I didn't stop there, but if you take the Fourier transform of a sequence that's been delayed by one sample, this right here transforms into that. So you get the Fourier transform of y of n, which is y of e to the j omega, and then the one sample delay kicks out the e to the minus j omega. And when you Fourier transform both sides of a difference equation operationally, you don't know what these Fourier transforms are. You just know operationally that little y becomes big Y with now a phase shift factor. You can factor the y of e to the j omega and x of e to the j omega out, and the ratio of those two is equivalent to then the frequency response, and that's from the convolution theorem, which says y of e to the j omega is x e to the j omega times h. So just spinning that around. And then for the case of the difference equation, we can see what h of e to the j omega is. And if I use partial fraction expansions, or in this case, my ears are popping right now, so it's getting really loud for some reason or another. I can inverse transform that term by term, and I can use the delay theorem on the second term, and I can get back to the impulse response if I want to, and other such things. But this example is 2.22, and it's mentioned a lot in the hints page. So you can make a lot of headway just with this all by itself and understanding some of the properties in there. My sinuses were messed up when I woke up, and this is a result of that. Right now, I sound like my right ear is blasting into my brain because it needs to pop. It's not going to go away that easily. If you have any questions, we need to get out of here before the next class comes in. But the hints are out there, so you can look at them, and you can ask me questions. If things go well, hopefully I can have some papers back by the end of the week. Meanwhile, I'm going to go up to the lab, and I'll take any questions up there if you want to follow me up there too. Because right now, the lab doesn't really need that much time from me, but whatever you want to do. I'll also talk about processing or any of the other things that may have given some of you problems in the homework, converting Markdown to PDFs and that sort of thing.